In this video we're going to prove the small angle formulae which were introduced and used in the last video. So we're going to prove the results that if theta is an angle measured in radians which is small, then sine theta is approximately equal to theta, tan theta is approximately equal to theta, and cos theta is approximately equal to 1 minus a half theta squared. If we start with a circle of radius 1 and centre the origin, and we have an acute angle of size theta radians, and we form a triangle based on the origin, the point 1, 0, and the point cos theta sine theta, which will also lie on the circle, then it's fairly clear that the area of the triangle OAP is going to be smaller than the area of the sector OAP. The area of the triangle, we can use the formula a half AB sine C to say that the area of the triangle is going to be a half times by OA, which is 1, times by OP, which is also 1, times by sine theta. So the area of triangle OAP is a half times 1 times 1 times sine theta. On the other hand, we know that the area of a sector subtending an angle of theta at the centre of the circle is a half r squared theta. R in this case is 1 because that's the radius of our circle. So the area of the sector OAP is a half times 1 squared times by theta. In other words, we have sine theta is less than theta. If we now draw in the tangent to the circle at the point A, and T is the point of intersection of this tangent with the line OP, then the point T has coordinates 1 tan theta. And we can say that the area of the triangle OAT is definitely going to be bigger than the area of the sector OAP. The sector OAP has area of a half times 1 squared times theta, as before. The area of the triangle OAT, well, the area of the triangle OAT is a right-angled triangle with a base of 1 and a height of tan theta. So the area of triangle OAT is a half times 1 times tan theta. And this now simplifies to give me the inequality theta is less than tan theta. So putting the two results together, we now know that if theta is an acute angle measured in radians, then the sine of theta is smaller than theta, is smaller than tan theta. Tan theta, we know, is sine theta divided by cos theta. So I can rewrite this inequality as sine theta is less than sine theta divided by cos theta. Dividing through by sine theta, which is positive because we're dealing with an acute angle, we know that we've got 1 is less than theta divided by sine theta is less than 1 over cos theta. This means then that the value of theta over sine theta lies between 1 and 1 over cos theta for any acute angle theta. If I let theta decrease towards 0, then I know that cos theta gets closer and closer to 1, so the value of 1 over cos theta will get closer and closer to 1. Now this means that as theta decreases towards 0, the value of theta divided by sine theta, which is we know is sandwiched between 1 and 1 over cos theta, must itself also get closer and closer to 1, because we know that 1 over cos theta tends to 1 as theta tends to 0. So if theta is close to 0, the value of theta over sine theta must be very close to 1. In other words, we've got theta is approximately equal to sine theta. Looking again at the inequality sine theta is less than tan theta, if I divide through by tan theta, I obtain sine theta divided by tan theta is less than theta divided by tan theta is less than 1. Now tan theta is sine theta divided by cos theta. Rearrange that tells me that sine theta divided by tan theta is equal to cos theta. So I've now got the statement cos theta is less than theta divided by tan theta is less than 1. If I let theta decrease towards 0, then I know that cos theta tends towards 1, which means that as theta decreases towards 0, the value of theta divided by tan theta, which we know is sandwiched between cos theta and 1, must also the value of theta over tan theta must also get closer and closer to 1. In other words, if theta is close to 0, then theta over tan theta must be close to 1. In other words, for small angles, theta is approximately equal to tan theta. Now, if we use the fact that cos theta is the square root of 1 minus sine squared theta, which is certainly true provided we have got angles which are less than pi by 2 and bigger than minus pi by 2. And remembering that if theta is close to 0, then sine theta is approximately equal to theta, tells me that if theta is close to 0, I've got cos theta is approximately the square root of 1 minus theta squared. Now at this stage, I need to remember about the general binomial expansion. Root of 1 plus z is the same thing as 1 plus z to the half. And if I use the binomial expansion for 1 plus z to the half, I've got 1 plus z to the half is approximately equal to 1 plus a half z, provided z is close to 0. Making use of this and putting z equals minus theta squared tells me that the root of 1 minus theta squared is approximately 1 plus a half of minus theta squared. In other words, the root of 1 minus theta squared is approximately equal to 1 minus a half theta squared. And what I now need to do is just merge the two highlighted statements to obtain the result that we were looking for, which was that cos theta is approximately equal to 1 minus a half theta squared, provided theta is close to 0. That ends our proof of the small angle formulae.